presentation, so it's going to be a lightweight presentation, so just relax and sit back, and probably we'll have some discussion. My name is Bing Wu. I'm a research associate from Karlsruhe Institute, Department of Technology and Management in Construction Process. So I'm here to present the work from my colleague, Dr. Svenja Lauble, und my former student Katharina Eisen and Dr. Hendrik Seibel. This work was done in collaboration with the company, software company Plan 4. They provide us valuable data and insights. So this is going to be an experimental using machine learning to predict the renovation cost. Okay, first I want to give you some numbers. It's in the context of Germany. So the first is about 60% of the building, the constructed before 1979. Why is that 10 point? Because after 1979, there's first building energy efficient law were in craft. So that's the building after that time was well isolated. So about 70% of the German residents need a retrofit. That's a very huge number. And it's the reason why the renovation cost prediction is so important. And so of course we know there's the building accounting for 30% of the CO2 emission in Germany. And the cost prediction is way complex than the new construction. Well, in the new construction, we start from zero, from just a white paper. We know exactly what inside of the building, but for existing building, we need first do a safe to find out what exactly materials in the building. Probably sometimes it's harmful. We must first remove it to be able to renovate the building. And in the literature review, we realized there's some research about predict the renovation cost for the building, damaged building in earthquake, but there's lack of research in prediction for general renovation. So that's our motivation. Here are some factors about influence and how these factors influence the costs. There's two main groups. The first is general influence. The second is building stock related influences. You can see there's a lot of factors that could influence the final cost. So let's jump to our research question. So we applied two kinds of machine learning techniques, regression and classification. And our question is which one is more accurate and how can we improve the trust in such forecaster to support our decision making? Well, we always say we need more data to provide a more solid prediction, but how much is enough? That's the question we want to find. And yes, I'm going to evaluate the machine learning approach for the early stage renovation cost prediction. So this is an overview data sites. We just use 100 project data. The reasons, well, the company provides tons of Excel sheets. There are a lot of them. It takes enormous time to process all data. So it took a few weeks to just process 100 project data sites. And they covering about 39 schools and 25 housing and 40 sport halls. And other buildings, they cannot be classified correctly. There are some mixed use. Well, there could be the first stage is for shopping. The second one is probably for renting. The last one probably for the third one is probably for dancing school. There's a lot of uses. So for the features, we we find the 14 features from the current data size, including the address, the construction year, the cost group, and the element group. The constant group, element group are classified based on the DIN 276. It's a German norm. And we also use the measures, the renovation measures, and the measure groups as features. And we also realized there's some information are missing. There is not even the roof area and the building height. That was amazing for us. We know we have some experts in this area. We know how important the two features are important. So we just extract this information from the OpenStreet map and to fulfill our data site. So X1, we basically separate this whole data site into two main groups. A and B. A just have 14 features. For the group B, they have 2 extra features. And we also want to know how exactly the number of data sites influence the final result. So, okay, these are our models used in this study. Regression or classification. For regression, we use decision tree-based regression, random forest, cat boost, and gradient boosting models, and the linear regression. That last one didn't work very well. And for classification, we use the k nearest neighbors. And to compare all the results, we use the mean absolute percentage error as a main error measure. And we also use cross-validation for robustness. Okay, that's basically the workflow. We start data cleaning, preparing. Took a long time. And first we just removed all outliers, and we also removed some rows with missing values. And for encoding, we use one-hot encoding and the label encoding and the feature correlation analysis. And we also standardize the data size using the mean of 0 and the standard deviation of 1. And we also choose some decision tree-based methods. And finally, we use optimal for the optimal performance. And the data is split 70% for training and 30% for testing, and across all models. With cross-validation k equal to 5 performed for robust examination. And that's our results from the regressions. And we realized from the group A, the results did improve when we increasing the number of data sites. But the group B is just like, okay, it's not that reasonable. When we even increase the number of the data sites, the precision is even decreased. And then for classification, that went even wild. The precision, the errors just increased, even in the both groups. That's our final results. For the regression classification, we just the best result is 7%. It's right there, but you see the number we use for that side is very small, so it's not a really solid result. And for the classification, that's 14% is also not that reasonable. So that's the result. Conclusion, random forest can boost provide best regression results, and with adding the extra features, we improved the accuracy, the accuracy a lot, but reduced the data size. While some in the OpenStreetMap, you cannot find out information about the roof area and the building height for all buildings. And the classification is used for comparison and filtering. Why we use the classification? Well, it's much easier to interpret. Well, we can say expensive, cheap, it's in the middle, so it's much easier to interpret. And the limitation, as I mentioned during the whole presentation, the data size is limited. It takes a long time to prepare all data size. And not all projects have the complete external data. Well, this data is basically used for the company to document the renovation projects. They are not prepared really for machine learning. So that's why we've done this experiment, to help the company to build more efficient data structure for the futures. Then they can really utilize this data for machine learning or the trainings. And of course, we haven't counted the inflation part and also the materials, the prices, they change a lot during the Corona period. In Germany, the material price just went crazy. And yeah, the funding is limited in Germany. So that's my, contribution. Yeah. That's basically for the company to prepare and to build a well-structured database, and for the future potential integration of machine learning techniques. And we also developed the pipeline that can be integrated into the current software. Well, the company, they already built their own software platform for a lot of renovation project documentation. And we also provide the practical data-driven tools at the early stage. Future work, we need much hard work to process the existing data site, and we want to still use and hybrid models to provide not only a reliable result and easy to interpret why the result, why is expensive or cheap. And we also want to consider the dynamic cost of factors, inflation, materials price, and the labors. So that's my whole presentation. Thank you for your time and attention. Thanks. So.